We live in a very complex environment. Complexity and dynamism and patterns are evident from satellite photographs, of videos. You can even see it outside your window. It's endlessly complex, but somehow familiar. But the patterns kind of repeat, but they never repeat exactly. It's a huge challenge to understand. The patterns that you see are there at all of the different scales, but you can't chop it into one little bit and say, oh, well, let me just make a smaller climate. I can't use the normal products of reductionism to get a smaller and smaller thing that I can study in a laboratory and say, oh, that's something I now understand. It's the whole or it's nothing. The different scales that give you these kinds of patterns range over an enormous range of magnitude. Roughly 14 orders of magnitude, from the small microscopic particles that seed clouds to the size of the planet itself, from 10 to the minus 6 to 10 to the 8, 14 orders of spatial magnitude. In time, from milliseconds to millennia, again, around 14 orders of magnitude. What does that mean? Okay, well, if you think about how you can calculate these things, you can take what you can see. Okay, I'm going to chop it up into lots of little boxes. And that's the resolved physics, right? And if I think about a weather model, that spans about 5 orders of magnitude, from the planet to a few kilometers. And the time scale from a few minutes to 10 days, maybe a month. We're interested in more than that. We're interested in the climate. That's years, that's millennia. And we need to go to even smaller scales. The stuff that we can't resolve, the subscale processes, we need to approximate in some way. That is a huge challenge. Climate models in the 1990s took an even smaller chunk of that, only about 3 orders of magnitude. Climate models in the 2010s, kind of what we're working with now, 4 orders of magnitude. We have 14 to go, and we're increasing our capability of simulating those at about 1 extra order of magnitude every decade. 1 extra order of magnitude in space is 10,000 times more calculations. And we keep adding more things, more questions to these different models. So what does a climate model look like? This is an old climate model, admittedly. A punch card, a single line of Fortran code. We no longer use punch cards. We do still use Fortran. Newfangled ideas like C really haven't had a big impact on the climate modeling community. But how do we go about doing it? How do we go from that complexity that you saw to a line of code? We do it one piece at a time. This is a picture of sea ice taken flying over the Arctic. We can look at all of the different equations that go into making the ice grow or melt or change shape. We can look at the fluxes, we can look at the rate at which snow turns to ice, and we can code that. We can encapsulate that in code. These models are around 1 million lines of code at this point, and growing by tens of thousands of lines of code every year. So you can look at that piece, but you can look at the other pieces too. What happens when you have clouds? What happens when clouds form, when they dissipate, when they rain out? That's another piece. What happens when we have radiation coming from the sun, going through the atmosphere, being absorbed and reflected? We can code each of those very small pieces as well. There are other pieces. The winds changing the ocean currents. We can talk about the role of vegetation in transporting water from the soils back into the atmosphere. And each of these different elements we can encapsulate and put into a system. Each of those pieces ends up adding to the whole. And you get something like this. You get a beautiful representation of what's going on in the climate system, where each and every one of those emergent patterns that you can see, the swirls in the Southern Ocean, the tropical cyclone in the Gulf of Mexico, and there's 2 more that are going to pop up in the Pacific at any point now. Those rivers of atmospheric water, all of those are emergent properties that come from the interactions of all of those small-scale processes I mentioned. There's no code that says, do a wiggle in the Southern Ocean. There's no code that says, have 2 tropical cyclones that spin around each other. All of those things are emergent properties. This is all very good, this is all great, but what we really want to know is what happens to these emergent properties when we kick this system. When something changes, what happens to those properties? And there's lots of different ways to kick the system. There are wobbles in the Earth's orbit over hundreds of thousands of years that change the climate. There are changes in the solar cycles every 11 years and longer that change the climate. Big volcanoes go off and change the climate. Changes in biomass burning, in smoke, in aerosol particles, all of those things change the climate. The ozone hole changed the climate. Deforestation changes the climate by changing the surface properties and how water is evaporated and moved around in the system. Contrails change the climate by creating clouds where there were none before. And of course, greenhouse gases change the system. Each of these different kicks provides us with a target to evaluate whether we understand something about this system. So we can go to look at what model skill is. Now, I use the word skill advisedly. Models are not right or wrong. They're always wrong. They're always approximations. The question you have to ask is whether a model tells you more information than you would have had otherwise. If it does, it's skillful. This is the impact of the ozone hole on sea level pressure, so low pressure, high pressures around the southern oceans, around Antarctica. This is observed data. This is modeled data. There's a good match because we understand the physics that controls the temperatures in the stratosphere and what that does to the winds around the southern oceans. We can look at other examples. The eruption of Mount Pinatubo in 1991 put an enormous amount of aerosol, small particles, into the stratosphere. That changed the radiation balance of the whole planet. There was less energy coming in than there was before. So that cooled the planet. And those red lines and those green lines, those are the differences between what we expected and what actually happened. The models are skillful, not just in the global mean, but also in the regional patterns. I could go through a dozen more examples. The skill associated with solar cycles, changing the ozone in the stratosphere. Skill associated with orbital changes over 6,000 years. We can look at that too, and the models are skillful. The models are skillful in response to the ice sheets 20,000 years ago. The models are skillful when it comes to the 20th century trends over the decades. Models are successful at modeling lake outbursts into the North Atlantic 8,000 years ago, and we can get a good match to the data. Each of these different targets, each of these different evaluations, leads us to add more scope to these models. It leads us to more and more complex situations that we can ask more and more interesting questions, like how does dust from the Sahara that you can see in the orange interact with tropical cyclones in the Atlantic? How do organic aerosols from biomass burning, which you can see in the red dots, intersect with clouds and rainfall patterns? How do pollution, which you can see in the white wisps of sulfate pollution in Europe, how does that affect the temperatures at the surface and the sunlight that you get at the surface? We can look at this across the world. We can look at the pollution from China. We can look at the impacts of storms on sea salt particles in the atmosphere. We can see the combination of all of these different things happening all at once. And we can ask much more interesting questions. How does air pollution and climate coexist? Can we change things that affect air pollution and climate at the same time? The answer is yes. So this is a history of the 20th century. The first one is the model. The weather is a little bit different to what actually happened. The second one are the observations. And we're going through the 1930s. There's variability. There are things going on. But it's all kind of in the noise. As you get towards the 1970s, things are going to start to change. They're going to start to look more similar. And by the time you get to the 2000s, you're already seeing the patterns of global warming, both in the observations and in the model. We know what happened over the 20th century. right? We know that it's got warmer. We know where it's got warmer. And if you ask the models, why did that happen? And you say, okay, well, yes, basically it's because of the carbon dioxide we put into the atmosphere. We have a very good match up until the present day. But there's one key reason why we look at models, and that's because of this phrase here. Because if we had observations of the future, we obviously would trust them more than models, right? But unfortunately, observations of the future are not available at this time. So when we go out into the future, there's a difference. The future is unknown, the future is uncertain, and there are choices. Here are the choices that we have. We can do some work to mitigate the emissions of carbon dioxide into the atmosphere. That's the top one. We can do more work to really bring it down so that by the end of the century, it's not much more than it is now. Or we can just leave it to fate and just continue on with a business as usual type of attitude. The differences between these choices can't be answered by looking at models. There's a great phrase that Sherwood Rowland, who won the Nobel Prize for the chemistry that led to ozone depletion, when he was accepting his Nobel Prize, he asked this question: what is the use of having developed a science well enough to make predictions if, in the end, all we're willing to do is stand around and wait for them to come true? The models are skillful, but what we do with the information from those models is totally up to you. Thank you.